And this is a bit smaller group, so this is great in the sense that you'll be able to ask more questions, be able to drill down deeper into the topics. If there's something that you're very interested in that we take more time, please let me know. Put your hand up in the chat group and we'll continue from there. So let me just start sharing my screen. Second. All right. So welcome to week one fundamentals. So the purpose of this course, and thank you for all for joining, this is the sort of the third cohort who have joined us to understanding how to really understand Gen AI. If again, you don't need to come in with a big IT background or understanding these things. Today, we're going to walk you through what these terminologies mean, break them down in terms of with a history of it as well, and bring it to where we are today. So before we start, there is some ground rules. So again, if you have any questions, please put your hand up in Zoom. I'll try to get them as soon as possible. Sometimes I may not be able to answer your question right away, simply because there may be too many questions being asked, and we have a time limit. We make sure we get through all the things we have for that certain week. So I may push those to the side, and we do have office hours. So if you have any questions that aren't answered in class, I may stay back after class to answer some questions, or if possible on Wednesday, if you want a deeper dive down a topic on our in our office hours, please feel free to join and ask those deep down questions. And sometimes those questions don't have to be related to the course to that week information specifically, but any more questions around Gen AI, just make sure you have that response as well. So again, you can use, if you feel too shy to ask a question, interrupt, feel free just to even just drop something in the chat. And I'll try to answer those as well throughout the class. If you see something like this, I'll read it and then I'll be able to respond as well. And that's it. So if you have anything that you like, again, feel free to give a thumbs up if you like something. All right, so Shima, I think you had your hand up first.
Everyone, good morning. I just wanted to know if you're going to share the slides
Yes.
after each meeting. Okay,
Yeah,
thank
so
you.
after each meeting, the slides will all be shared and the recording will be shared as well. BJ, you had a question?
Yeah, actually, I also had a similar question. So can you like emphasize when we need to take any extra notes or something like, because the slide, whatever the information on the slides, you'll be already sharing, right? So, but you can emphasize anything that we need to take notes.
Yeah, you'll see pretty soon. Once we get to, I think today is more me talking and presentations than actual
Oh,
coding and doing things like that. So today is more of a lecture. So there's
okay.
gonna be a lot of knowledge drop. This tends to be the one that gets rewatched a lot because I'm going to go through a lot of terminology and terms you may not heard before or interested how things are working. So this is probably the one that you probably need a pen and paper as I go down like during the second half of the course.
Oh, sure. Also, I don't know whether it's useful or not. So, do we need to have another laptop for practicing and when you are presenting, or what's your suggestion? Which one is the best going forward when we are actually like doing hands-on?
For sure. So I think by starting next week and that we start doing hands-on, you don't need to have a separate computer. You can use simply, what we'll do is we'll break into different rooms. You'll be put into maybe groups of two, three, and you'll be able to work on coding things together. And that's when I'll be jumping into the rooms to see if anyone needs help or anything like that as well. So you don't have to be worrying about, oh, do I need to have a screen open for coding while he's talking, things like that. I'll usually do code walkthroughs as well. which I'll have the screen open, have the code open there, and you can run it at the same time I'm running it to ensure that everything is working fine for yourself. But yeah, so don't worry about that as well. So
Thank
well, you'll have dedicated time, so you don't have to be worrying about writing notes and coding at the same time.
thank
So just on that note, we'll be giving out sort of a prerequisite in terms of where you can go look for the codes itself. So everything's written for you. So again, this is a 101 course. I don't expect you to build everything out from yourself. If this is your first time looking at Python, this is your first time learning how to build something with GenAI, this is exactly the course for you. You'll get the basic templates and frameworks how to and how to build certain basic applications. All right, so if no more further questions on course etiquette, things like that, then let's start. All right, so you hear the word, I'm not sure if you guys see in the news, there's a lot of things that people are saying AGI, 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 right? So what does the AGI mean? And how is this connected to what we have today? So there's different ways how you can measure intelligence through the computer. So there's three different ones that we definitely talk about. So one, artificial narrow intelligence. We call this sort of a weak AI. So it's good to understanding and process lots of data, but however, it can't make independent decisions, new skills, or develop understanding of the world. So it relies mostly on pre-programmed algorithms and requires humans to operate. So an example of a narrow intelligence could be that you write a SQL code to extract data, and if you see if column A is equal to column B, then this out, right? So it's smart enough to know, understand your rules, smart enough to understand your code that you want to extract from the data and get the things out, but it still requires you to write that SQL code, still requires you to tell it which columns need to be coming in, and things like that, right? So it's not going to give you output that way. You have to sort of feed it everything and then it will do. So we call that ANI or artificial narrow intelligence. And sort of mostly where things are right now, right? So everyone talks about AGI. So where we are right now, I think we're between the middle of ANI and AGI. AGI is when you have something that's completely independent, strong AI, can understand, learn, apply, and everything at a human level range. So it has to match, even surpass human comprehension. So the problem with LLMs today is that they can be super smart and answer university type questions, but it comes to common sense questions, they still fail on certain areas. So again, for our AI to be as top as AGI, it sort of needs to be a well-rounded, more well-rounded in terms of intelligence. So where we are right now is in terms of our technology trajectory is between the ANI and AGI. And then once you get to AGI, which is a general computer, then becomes a super intelligent, right? So I'm not sure if you guys seen Iron Man, you have Jarvis, like super intelligent across all devices. And you have this machine that's able to learn, adapt, and be able to do things without human intervention and is completely autonomous. So that's what we call artificial superintelligence. So a lot of hype is going around AGI saying, hey, we're already there, so be careful, like this is the end is coming, etc. So there's a lot of people who are trying to jump on that bandwagon, but right now we're currently not there yet because there are limitations to how LLMs work. In today's class, we'll break down how these LLMs work, and you'll see why we can't be at AGI just yet. So the word AI, you might see it being used commonly everywhere now. Like this is AI, this is AI, but they're sort of using that term very broadly. AI has been around for a while, and we'll talk about since when, and we'll go through those terms. But when someone says AI, people have been talking about AI since 1940. People have been talking about AI way before then and develop things that are AI. So how can someone in 1940 talk about AI and then in 2025 we're still using those same terminologies? And simply because artificial intelligence, generative AI, which what we're seeing today, is not pure only AI. It's just one domain inside the AI landscape. So when people normally say, "Hey, I know AI, it doesn't have to mean that you're using LLMs. It could be machine learning. So again, going back to data science, doing predictive modeling, could be deep learning, could be using neural networks, being able to learn different things like that as well. And then there's generative AI, which is all different subsets. So that's one thing I just wanted to have a big gripe with when people are just saying, well, this is just AI. But what they really mean is just saying that's generative AI, which is different from all these different types. And the reason why we call generative AI to LLMs is because they generate text without human intervention. So this is what we call it Gen AI because it generates text, these LLMs, and they're all part of a subset. So you'll quickly learn how LLMs or generative AI is actually an advancement from machine learning, an advancement from deep learning, and then generative AI is an advancement from that. So, like I said before, don't worry about taking notes this one. And again, I won't be reading everything that's on these slides. These notes are like sort of your textbook. So to give you good definitions of what this is. So again, some of you might be new to data science. Some of you might not understand what is really machine learning, deep learning, all these different areas. But in data science and AI, there are multiple things there are different models, different ways how to measure, not simply just using generative AI. It's when you say the word AI, it's automation. So what are the things that we can automate? So one of them is machine learning. So machine learning is imagine someone who has a statistics background and then combine that with a computer program, be able to use statistics to determine be able to predict future outcomes. And that's basically what machine learning is. You're trying to use statistics and computer programming to determine the best outcomes for certain situations. And that's what machine learning is in that total sense. And again, that is part automating it because again, you're having people who know statistics, who know computer programming, and they're developing these models that say, well, look at your historical data, based off your last 500 customers, your next 200 customers. If you change one thing about them, this could increase your sales. So using machine learning more in terms of businesses, machine learning is part of data science, it's all part of that data science technique. But you're using that statistics to really get and drill down more to get it. Um, so machine learning is one subset. The next subset you have is deep learning. Deep learning is again is using it takes it to a step further. Okay, now we have statistics, now we have computer programming, we can develop these models. But what if there's a way that you can have these models iterate over different things, and right? So let's say you have let's say again, let's say you have that model that looks at your previous 500 customers. So now you can then create another statistical model that will go over and iterate over your customers what different types of attributes they have and try to say, okay, if this attribute has this, then do this. This attributes have this, do this. And you put it in a loop and you put it in a loop and you put it in a loop. And then finally, when you put it in so many different loops, the computer itself can actually see patterns and recognize patterns from these different loops that are going through each other. And that's when the computer can recognize these patterns, that's something called deep learning. So you're developing these neural networks, which is a term that was developed in around 1950. These neural networks are ways to actually learn about behavior, be able to learn about certain patterns, and using statistics and mathematics to sort of understand that more. So once we got to sort of that type of that learning, next we learned about, okay, we know about statistics, we know about math, we know about computer programming, but the English language is very hard. Or any type of language is very hard. But what if there's a way we can then use our statistical background and computer knowledge and apply it to language? And this is where NLP was created, so natural language processing. And they found that if you could assign numerical terms to the alphabet, to certain words, give more weights to certain words and more attention to certain words, you can sort of have models that can look for certain words that are very common. So before Gen AI came out, a lot of these companies and a lot of these that are using we're using NLP or natural language processing to go through and sift through phone calls, to sift through chats, through histories, and be able to look at it and then, okay, you know what, this conversation is talking about shoes. This conversation is talking about math. Because when you're able to assign, we'll learn this about more, learn about more about these different types of codings, but once you're able to assign these numbers to these letters to certain words, they found out that you can create statistical models now because now it's not words anymore, it's math, and then math becomes statistics, and you can then you can determine the probability of things once you have them into numbers. So you can say, well, this person's going to say this word afterward because king is usually a male. So if you know that king is male, then therefore, if someone says, what does the king want? He wants this because you know that the king is male. Male's a very high probability that it's a king. So therefore, you can use the word he because that's attached to male. So you start assigning language code, you start assigning rules, you start assigning things like that. And that's where NLP comes from. So then someone thought about it and said, you know what? What if we grab NLP that we have and then combine it with our deep learning, which is again going through iterations, learning per learn, what could happen? And then this is where we have our generative AI today, or LM models, which we're grabbing these statistical models that are looking over certain words, which words need attention, and then combining it with deep learning, which is going iterating over. We created a model that actually can generate text now from previous conversations. So to me, it's more than just an autocomplete. It's actually, again, what's different between autocomplete and a large language model is that an autocomplete is just doing statistical probabilities of this is what you might say. But remember, deep learning goes deeper than that. It looks through millions of different loops and iterations and variations of why something could be. So when someone said, I want to buy new shoes, when you add deep learning to this, you're like, okay, what kind of shoes would you like to buy? An autocomplete wouldn't be able to understand your context. An autocomplete won't be able to understand what you're looking for. A deep learning model is trying, it understands it. Looks like shopping shoes. So then come out with the next best way of saying what are the next best ways of looking for shoes are. And we'll get deeper into that, but those are really the key terms and basically what you need to know about AI is that all of it is sort of a progress of each one building on each other, each one sort of developing with one of the other to where we are today, and which are LLM models, which are part of generative AI. So LLM models you might see today are examples of ChatGPT, Llama from Facebook, Claude from Anthropic, etc., and Grok from Elon Musk. Remember, so there's different LLM models out there today that are part of this generative AI sector. So I'm going to take a pause there. I know I spoke a lot about any definitions, but this is basically why AI isn't just simply just AI. It's when someone says I usually pause and okay, what do you mean by AI? Are you talking about machine learning? Are you talking about NLP? Like, no, I mean like the ChatGPT, like, oh, you're talking about generative AI. Because again, AI is a term that we'll talk about before that has been there since it's been there for a while. So I'll pause right here. Does anyone have any questions around the definitions and what they mean and how we are where we are today? Okay, perfect. So everyone's gonna do really good on the quiz. So no, so I usually do a Kahoot quiz, which is pretty much like a competition within everyone to sort of understand certain terms and things like that, just to make sure you're capturing the information. So again, I tell people just make sure I know it's early, it's 8 a.m. Make sure you have your coffee. AI is not a fun terminology to talk about at 8 a.m., but make sure it's again, the purpose of this quiz is just to make sure you're capturing and understanding what really these terms are and how they're actually applicable. Okay. So let's go back and go back to that term, right? So remember I told you that AI is not a new terminology. It was actually first named in 1956 at a conference. So we're talking about more than 75 years ago. And that's when the first digital computers were happening, right? And then 1950s, we talked about learning models. So again, those neural networks were being proposed at that time. We're even talking about 75 years ago. So again, this isn't something new that just came out recently. And we're saying, oh, AI is doing this. This is something that, again, has been out there for a while. The only thing that's new that's happened recently, since 2018, is the Gen AI models. The Gen AI, remember, that's a subset of the whole AI side. So again, there's different types of ways to do things with Gen AI today. So because we got used to writing, we're like, okay, but what if we add a picture? And we found out that if you grab a pixel from a picture and you can actually decode each one to a binary number 1011, the next pixel is 1022, 1033. It uses, so then you find out there is a pattern of, okay, so if I use these binary symbols, I can make a picture of a dog, or if I use these binary symbols, I can make a picture of a cat. So really, it's then we found out if you can use binary to music, if you could do the same thing with videos, etc., and completely convert them to numerical symbols, you actually can use statistics and models to sort of develop that as well. So it was sort of really a big breakthrough, and this is why we have different things. That one for writing, one for audiovisual, one for art, and one for code. So someone wrote in the chat, was a really interesting question. So does all AI use neural networks? That's a very good question. So right now, the models, so the difference between training a model and having a live model. And we'll go through that in a bit. But to answer the question, in order to have a generative AI model, you need to train your model using neural networks. And we'll talk about those in a bit, in order to make it smart, in order to have it to have those benchmarks. So when you're talking with a ChatGPT, when talking with those, they're not using neural networks to respond in that sense, but you use neural networks to train them to be smart. So during the training process of these AI models, they use neural networks, but not during the conversation chats you're having with them. That answers your question. Okay. So again, neural networks isn't something new either. So neural networks actually was done by a mathematician, John van Neumann, and this was done in 1940, all through a chalkboard in Stanford, I believe, that he started thinking about what could a neural network look like. And he sort of built this out through a mathematical proof. And because he threw a mathematical proof of what a neural network looked like to learn, they used this and designed the structure of a computer that could store data and create programs in memory. And that's when really neural networks started happening. So because we understood that a neural networks could happen, the 1950s, computer things were started evolving, right? So we know that time, there was a famous person named Alan Turing started happening, and he started getting deeper into the mathematics understanding of neural networks, and he used these neural networks to do cryptography, right? So again, during the war, there was a lot of encrypted things that could be hard to be cracked. But using neural networks, understanding that mathematician Alan Turing used those, created programs or created software that could break through these codings. He started getting scared of these things, right? So he realized that Alan Turing in 1950, again, we're talking about 75 years ago, that hey, if I could build a machine that can crack and decrypt really hard responses, how easy is it now for a machine to actually determine if it's actually human or not? So again, in 1950, he developed something called the Turing test, and there are three questions you would ask an AI to determine what if it's actually human-based level or not. And that was something called the Turing test at that time. And that was something that people thought about even 75 years ago, not even having generative AI. In 1956, Dartmouth College at that time, I think it started doing something called logic theorist, which is a mathematical proof. And how this is important because this logic theorist helped start developing algorithms. So this is where we have algorithms happening between 1950 and 1960. And you have something called GPS, not the GPS for your phone, but GPS, this one's called the General Problem Solver. And it's still, again, it's AI programming using neural networks, using logic theories, and actually starting to understand that, hey, this actually could solve lots of problems. Then 1970s, 1980s, we started using these different techniques to start understanding things about more. And then 1990 to today, there are many different companies that have started building these supercomputers that are able to process things, large of data, and be able to understand it. I think this was the first time in 1990 as well. IBM created something called Deep Blue, and that defeated the first Russian chess master around 2011 using computer techniques. So again, the evolution of how computers were getting smarter and how things are done are sort of based, again, really on human interactions with these AI models, programming them using different mathematics, statistics, and computer programming to make sure that they're getting these responses and they're getting these outputs that they're looking for, right? And they're trying to develop that really smart AI. So what's happening today? So again, in 2000, we talked about in 2011 they built that chess master beating, but in 2000 they developed a robot that can do vision. So again, going back to the imaging, if a robot could take a picture of its surroundings, could it really digest it into numbers and understand what's happening? So in 2000s, the first robot was created that could actually stimulate and recognize human emotions. In 2009, we know the driverless car happens. And again, this is all using vision models and programming. 2011, we started having voice models. Siri was released using Apple. And what's really the first breakthrough in generative AI actually happened in 2018. And this happened from Google's DeepMind. But they invented something called BERT. And BERT is what we'll talk about later on, because there's a lot of definitions happening right now, but we'll do more. But the BERT model was sort of the first way of how we can actually break down languages and categorize them. So going back to NLP, in 2018 is really the breakthrough for NLP, natural language processing, of using these models to represent language and be able to get some good outputs from it. And then from there, ChatGPT learned from Google's their deep model and built their own model called GPT-3. It started GPT-1, and then did GPT-2, and then as we know, GPT-3 came out, and that was sort of the first generative AI that is actually when you would talk to it, actually would come back and give good responses. Then we know that driverless taxis are having rides in San Francisco down in 2023 and 2024. We're seeing a lot of things that are emerging just from this, right? So AI has been changing a lot of different things, and just giving you a sort of history of it's not just simply just about having conversations. It's also about AI in terms of vision models, voice recognitions. Everything is sort of evolving all around this. Okay, so again, trying to make things clear. So the difference between data science, AI, and ML. I know I use the word data science, and again, if this seems to be very repetitive, I'm just trying to make sure you understand the concepts. That the point of data science is the process of extracting meaningful, useful insights from volumes. So you would say I'm using data science is when you're using these ML models to solve a business problem. So when you say, oh, I'm in data science, so you're using statistics, you're using ML, using some sort of AI that is using to develop real world business problem solutions. When you would say, I'm just doing AI, that's another branch, like I said before, is a subset. We saw before in that huge circle. And the whole point of it is of AI is to make humans and machines think and act like humans, right? So they make decisions on their own. That's when you would use the word AI. And then use ML, which is a subset from AI, remember from that big circle, is to use data and algorithms to make sure they learn better and to make more AI better decisions. But when you use ML for business, that's when it becomes data science. So again, I just want to make it clear that when people throw the terms AI, ML, data science, blah, 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 you know, sort of know the difference between what's happening. When people say data science, oh, it means they're using machine learning models for business. That's what data science means. Oh, I'm talking about AI. Okay, that could be robotics. That could be vision models. So when, like I said before, when I see all these posts like, oh, AI has a big breakthrough, but it's really only talking about generative AI, we know that generative AI is only a small subset of AI. So again, it's very small that way. Okay, so what's going to happen now is, like I said before, hopefully that you had some of your coffee. We'll go through a small quiz of you, if you be able to understand sort of the concepts of of different types of terminology and be able to go from there. So it's really simple. All you need to do is um, simply use your phone. You can use your phone and scan the QR code on the screen, or I'll put the link in the chat as well, and I'll be able to put the game pin for you. Okay. So if you just want to go, it's www.kahoot.it. Let's put the link in the chat. Or you can scan the QR code on the screen. Okay, perfect.
The QR code doesn't seem to be working.
Okay, and the one on the screen. Okay,
Yeah.
let's click. Yeah, if you can just click on the link, hopefully that will be better. There's only 10 of you guys, so I will pick on. I will start picking on you guys. The game pin's on the screen. If you're able to see my screen, 6777787.
We are still seeing the Kahoot quiz screen, Louis, if you're sharing a different screen.
I switched over. Okay. We're gonna need two more, and then we're good. I think that's everyone then. Oh, perfect. So let's start. So the faster you respond, the more points you get as well. All right. So as we talked about before, only generative AI can actually create new information, right? We know that AI is focusing solely on making sure that it can mimic humans, deep learning is built using neural networks, language models, understanding it, but only generative AI is about generating new and unique content. Right, PG. All right. This one should be easier to get a little information on this one. So remember, I just gave the answer before on the previous question. AI is to act like to have human-like intellect, right? And be able to use things without human intervention. So that's what AI is. That's what it is. People got confused with language models. So language models do not have human-like intellect yet. They are text probability. There are text probability things which we'll go through later on today. But you'll see the difference between what really AI should be versus just like a language model. Oh, we got a new leader. Wait, Jeannie, take it over. All right, so almost perfect on this one. NLP, natural language processing. Like I said before, they realized with machine learning models, they're able to get good predictions. Like, what if we then used it on language? And that's what NLP is about using the statistical things on languages, and that's why NLP is able to modify that. Okay, Ishi, we got three in a row, so she's on fire. Let me show next. Okay, so that's a good one. So remember, machine learning is the top part that uses statistical methods and algorithms to gain insights, information from data. And when you would go from deep learning is when you see it actually learning from this data and actually be able to comprehend it, right? So the difference between machine learning is it will try to use statistical methods in order to determine the best outputs and get that information, but it's not going to learn what's happening in your like it's going to understand previous interaction, but it's not going to learn it. Meanwhile, deep learning is when you're actually understanding the real context. And machine learning, what it does, it converts everything to numeric values and then uses statistics to determine what could be the best output. And deep learning, it actually understands the context of what's happening in order to understand what's more. So that's why the answer is A. Alicia's still on fire. All right, I think this is the last question. So yeah, so I just sort of gave the answer from last time. Remember, deep learning is looking for ways to understand, right? And replicate what's happening. So deep learning is the right response on this one. Um, yeah, so that would be that one. Right. So who is the winner for part one? She got high points over 3,000. Good job. After as well. Awesome. And number one for this project is Marisha. Congratulations. BJ Regini, you were super close. Okay. Screen's on. Okay. All right. So I'm gonna pause right there. If anyone wants to go take a quick 1 or 2 minute break for like a water, things like that, we can start again in the 46-minute mark. All right. So we'll take a quick pause and we'll start in about 2 minutes. Okay. All right. We're back. All right, so they told me to give you a heads up when you should be writing notes. So this is going to be sort of the most dense part of pretty much the whole course, what we'll be going through right now, and which we'll be going through the basics of how LLMs work and how they understand things. So again, this one's gonna be a little more dense. So I may be going over things a little fast. If I am, please feel free in the chat if you don't understand a concept. Please also remember that if you missed a part or you had to step away for a bit, don't worry. There is that recording that's going to be recorded, and you can always loop back on the office hour to understand a bit more. And don't be embarrassed to get a step away. Things happen, and that's life. So we're just grateful you guys are joining us, and we get into it. All right, so let's get into the different types of large language models. So how do these LLMs, ChatGPT, Gemini, how do these work? And why are they two different types? So they found that the more information you can then give an LLM, the smarter it was going to be. And this is where the neural networks and deep learning comes from. Imagine you had 1 million rows of data that's pre-trained that says anytime that you see hair, nose, furry tail, and a collar and can bark, that means dog. Or you grab different information and you just train a model with different things. So what ChatGPT did, which they're in hot water for when they first started, was they went on the web and scraped everything they could find. Like they went on web, scraped Google, scraped Reddit, scraped Twitter, scraped anything they could find on that type of information, and then tried to feed it to a large language model or to a language model and say, I'm going to train you on this using neural networks in order for you to be smart. So when you're grabbing all that information, and you're training a model on this, the model will take time to learn. So some of these models took weeks, months to train in order for them to have certain concepts. Now, how much data goes into a model, that determines the type of language models there are. So we have something called LLMs, which are large language models. This is why you might hear the term LLM or generative AI, because These are these are language models trained on larger data sets, and they use deep learning and transformers to analyze complex relationship between words. So you probably don't know that you're talking to a large language model, but ChatGPT, a large language model, anything from Gemini, anything from Google, these are large language models. The Claude models are large language models. These are models that have been training on trillions and trillions of data sets. So these things are huge and they are proprietary. So you don't know how much information has gone into them, how long they trained them for, and the cost of training them. They don't disclose this information. So when you see something that says Llama 405B, that means a language model has 405 billion parameters for it to understand how well it's working. Or we see something that's called 70B or 70 billion parameters. These are the types of parameters that you would see in large models. So they are computationally intensive. These cost hundreds of thousands to millions of dollars on training them. And again, this is where you need to have a large interface to do this for. Next is you have small language models. So they found that, okay, I can feed a language model trillions upon trillions of data, but guess what? What happens if I grab an LLM and tell it to then distill me information that is exactly just cleaned? So what does that mean? Let's say in the large language model, it was trained to had maybe 3,000 documents on cats, on what cats should be. But when you tell a model to distill it, maybe they could drop it to only down to 20 rows of data and which are specifically trained for a model to understand. And therefore you don't have to train it on 3,000 documents of data what a cat do. You train it on only 30 prime and really clean examples. So I don't know if you guys heard, there's a Chinese model that came out that sort of disrupted everything. And that was sort of something called DeepSeek. Now, ChatGPT and Gemini, on all these different models, are trained using thousands of these really high-performance graphics cards, computational resources, etc. And NVIDIA stock was really, really high because you say, okay, if LLMs are the future, you need to have these graphics cards. You need to have the computational resources in order for this to happen. But DeepSeek, what they did was they trained on ChatGPT's data and distilled the information from its model. So although ChatGPT may have been trained on trillions and trillions of data, they probably trained it probably on a million or 2 million to up to 5 million data set and made a smaller model that didn't require as much computational resources as ChatGPT did and was able to produce just as good under that at that time responses. Some people even prefer it better. So instead of using $5, $6 per hour, let's say per minute to use one of these resources that are super highly intensive, they have these smaller model, again, going to these smaller models that have been trained on smaller data sets, but are more clean. And these cleaner data sets meant that it's cost way less to use it. And because people saw, wait a minute, you don't need to have 1,000 graphics cards to train an LLM model and it has to be done over 3 months or 2 months. You can do it with only 50 in about 2 weeks. This is why NVIDIA stock crashed as soon as DeepSeek came out, because these models can now realize, hey, actually, I don't need 3,000 documents about cats. If only for that 3,000 documents of cats, 20 rows are actually what it needs. And then why do I need to invest more in graphics card? And this is why we saw NVIDIA talk stank. Because this like just went right down, right? Because they're finding that you don't need to have a large language model in order to have just as accurate results. They found that these smaller models, these small language models, are providing just as good responses as the large language models. And so what? Maybe it's not 85% correct. It's only 70% correct. Well, people just can justify, you know what? If I can only spend $100 a month using LLMs, my computational resources, versus 1,800, and I'm only getting 15% or 10% less accuracy, that's a risk I'm willing to take, right? So people are now realizing you don't have to spend as much in order to get as good results. So, and someone asked you, can you give me more use cases for SLMs? So an example of a use case you can use for a small language model is, let's say you have a computer that only has 16 gigs of RAM, like a typical computer, and you want to run on LLM locally. Now, if you were to run Llama 70B parameter model on your computer, you need to have at least 80 gigs of RAM or virtual, no, sorry, 160 gigs of virtual RAM on your computer. You need to have computational space. You need to have at least 400 gigs of SD, well, 500 gigs of SD RAM, and be able to have it run fast enough for you to even load that model. Meanwhile, a small language model, you can do Phi 2. One example I have here is 1B. You can load this on your computer with 16 gigs of RAM and not have to have extra resources and be able to run at a good speed and be able to have just as accurate results. So be able to run something locally on your own computer and be able to use things are a huge people want that because again, people respect privacy. They don't want sometimes they may not want an LLM that's being run through the internet, have all the information. They want to host a local LLM on their own computer and be able to interact with one of these smaller LLM models. And a lot of businesses tend to want that. They want to run their own local small LLMs because they don't want they don't want the company information being sent to OpenAI, or they don't want their information being sent to Google. They don't want things like that as well. Although they might have SLAs, sometimes they still don't trust them. This is where small language models would come in and do the work. So again, you don't, and sometimes it's just overkill. We know that sometimes that LLMs are really good at language, like they're built for language. They're not built for mathematical computations. They're not built for writing extensive essays at a PhD level. But if you were to say a sentence and say, I want you to classify what this document, what this line means, you don't need a large language model that's trained on 15 trillion dots of data for it to say, oh, that line's talking about pizza, right? It could be a small LLM that's already been trained on a really clean data set, and it could quickly classify things for you that you don't need a super large language model to do, and you would save yourself a lot of money going down this way. Another example I'll quickly give, just through time, is that it's way more cheaper to train a small language model than to modify a large language model. So again, we'll talk about what fine tuning is, but some companies, they tend to want an LLM to have knowledge about their business. And because their business stuff isn't online, right? It's all in your repository directory PDFs. You can fine tune a model, which we'll talk about what fine tuning is, but you can train a model that's already been trained to learn more about your business. And the cost difference between training a small language model versus training a large language model is substantial. I mean, it could be up to $500 to $600 to train a small language model. But it could be up to $12,000 to $15,000 to train a large language model. So the cost is astronomical once you want to start training the different sizes of these different models in terms of a business aspect. So this is why a lot of people prefer using small language models. I give you some examples here for you guys to look at, go online to use it. So the purpose of it is to use fewer resources. They can be hosted locally with minimal process capabilities, and they were designed to be more accessible and practical for specific tasks or domains with little computing complexity. So hopefully that gives you a good overview of the difference between a very large one and small language models and when you would use the one or two. Of course, if you're trying to ask how to break a genome sequence in a DNA data set, you probably want to use an LLM model that has more reasoning than a small language model. That way, you probably get more accurate results. Okay, so again, we just explored what are small and large language model. So now let's get into specifics. How do you train these models and how are they made? So they're made based off transformers. And we'll go through different types of transformers on the next slides, but these pre-transformers are called GPTs. So it's no coincidence that ChatGPT used this in their name in their model, but GPT stands for Generative Pre-trained Transformer. So remember someone asked the question, is neural networks being used when you ask an LLM? They're not being used when you are writing something and it's working on its background, but it's used to train a model. And we'll talk about that under the generative. So we'll talk about that next slide, but we'll talk about understanding that GPT stands for Generative Pre-trained Transformer. So these LLMs that you're talking to are pre-trained transformer models that have been given data sets that are cold. And when I say cold, it means that these LLMs do not update itself. So if you trained a model from all the information from 1995 to 2002, and you ask who is the president of the United States, it won't say President Trump is the current president today. It will say who the president was in 2022, because the models only know and understand the data set that it has. They're not trained on anything else. So going back to the AGI part, they depend on us to give them the information to be trained on. They're not reliant, they're not self-learning. They don't grab data, import it back into itself, and then continuously learn. Large language models are not designed to be like that. GPT they only are trained once on one specific data sets and do not learn or evolve from this. So again, I just want to make sure this is why um, I try to steer people away that we are not at AGI yet, because these models are are trained on frozen data sets. In the last cohort, someone challenged like, well, if I go to ChatGPT right now and I ask what day is it today, or ask what president is going to give me the information, and like, yes, because what people have done now is they're able to do something called tools or connectors, which it can send an API signal out to the internet, retrieve information, and then show that to the LLM and use that as the current information. But it doesn't mean that the LLM, if you remove those connectors, would know the information, and it won't know that information. Sometimes you'll see when you write ChatGPT, sorry, my knowledge cutoff date was August 22, 2024. I don't have any information after that. But now, because we have something called web connectors, we can connect these LLMs to the web and get more information. But if you didn't have that and you just download an LLM from the internet and you want to play with it, it will only do information based off that knowledge cutoff date. And so again, I say use these models responsibly and acknowledge these specifics. Do not be fooled and be think that it's going to constantly evolve. Hey, it's knowing me. It knows everything. It doesn't learn or evolve during interactions. It's just strictly generative model in that type of sense. I'll stop here at any pauses. Anybody have any questions of the limitations of these LLMs? Yeah, I think everyone's giving up. I expect everyone to have perfect on the next Kahoot score then. That's awesome. Okay, so now we're gonna get a bit more technical. This is what I said before. This is probably the most heaviest in terms of density of understanding the architecture behind these transformers, um, and how they work and how we sort of evolved to what we have today. So understanding this, so going back to the big circle we had that AI was there, right? And under AI, we had machine learning. Under machine learning, we had neural networks. And then under neural networks, we had generative AI. So these are examples of three different types of neural networks that happen, where an information goes in, it learns based off a notation and outputs information. And there's different types of neural networks. So example, it is showing you that that once a recurring neural network happens, like goes through here, learns it, goes through the loop, goes through and keeps learning. There are different ways of you can actually go grab a word and break it down. So this is just showing you the history and sort of the knowledge of these different ways how to train an LLM, how to train a model before an LLM structure was coming out. So when you're talking about learning words through NLP or going through some learning networks, there's different ways we can do is have it focus on certain words. You can actually have forget words that aren't that aren't important, like vocals like a, ah, or to, or whatever the whatever it was, things that are sort of stop words. Forget those because those are really important. Get the input, relearn it, try again, and then give an output, and then go again, revert it. So again, it's showing you the different examples of how neural networks are working and how we sort of looked and evolved different ways from recurring neural networks to LSTMs to GRUs until now what we have something called a transformer. So remember I told you in 2018, Google invented something called a BERT model, which we'll talk about next, is this side right here. They created a BERT model, which is able to do a one-directional understanding of words. So let's say they had a model that was trained on 600,000 data sets, all about different products of a bank. When you would run a BERT model on it and you would say, okay, look at this conversation this agent had with a customer, classify what this is about. So this would go into our transformer model on the right side and look at it, see what kind of words are being said, and then gives a classification and say, okay, they were talking about a gold visa that they were looking for. So the output would just be called gold visa. But one thing to note is that it's not generating new text. It's the whole point of it, the BERT model was understanding it. What we learned later on is that GPT learned that you can add an extra layer, which we'll call encoders, that can actually teach it to learn new words. And that will take us to the next slide. Okay, so when you have an encoder and a decoder, there's two things that are working at once. So this is how you would train an LLM, and this is how it works. So when you have a GPT, a generative pre-trained model, you will only have this right side. But during training, you have to have your encoding side. So this is where you see it. This is how a transformer would work. You have your encoder, which is reading information and teaching it. And then you have your decoder, which is the right side, which is then being able to look at words and generate things and generate information. So I'll be going talking about different terms. Don't worry, we'll be going through every single thing in this different areas and understanding this. So again, this might be a lot of information at the front, so don't be intimidated on this side, but we'll be going through each of these different things and what they understand, what they mean. So one thing right now I want you to focus on is that we have an encoder and you have a decoder. And all LLMs right now that you have gone through this sequence. They have gone through encoding, which is training the model, and then it gets information then gets fed to an LLM, and that's what this right side is your decoder. And this decoder is the one that answers and asks your questions from that side. Okay, so before I get into it, we need to take a step back and understand a little bit more about how each of these functions work and understanding a little bit more about NLP to really understand what's happening with a large language model. So remember I talked to you about before, the computers are best at understanding numbers. So words are converted into tokens, which are a numeric representation of the words. And then these tokens are provided as inputs to the AI model. Not sure if you guys seen on AI Studio or on ChatGPT and different things like that that said they have limitations of how much tokens actually go into a model. So what tokens are a count of words. So example, I walk to the store could be a count of 8 tokens because it counts one or two words. Usually two or three letters counts as one token for an LLM model because it uses that to make a representation. So you have to understand the word tokens is a very common use word when understanding generative AI. And this is something I need you guys to understand and use it because not only you'll be able to use it in this course, you have to be using it, you'll be using it constantly in the future to understand that there are limitations of tokens. There's something called a context limit, in which an LLM can only understand up to, let's say, 40 pages of a PDF. Meanwhile, there's other LLMs that can take a whole book of Harry Potter and be able to understand it, because certain LLMs are built differently and take in tokens differently. So although, let's say you have a paragraph that you write, is 120 tokens for ChatGPT, but when you use it for Gemini, it could be 200 tokens. So each one has their own way of counting words to numbers. So every single time you work with one, you sort of have to understand how that tokenization happens. So in order once the words are represented as tokens, which is converting words to numbers, then these happens is that it becomes vectorized. So as I was saying before, the best way we know how to use things and be able to predict is convert things into statistics or mathematical concepts. So again, if you remember physics class, you can vectorize things. So what does vectorization mean? If you take you back to maybe grade 10 physics, when you have something vectorized, it means it has direction, right? It's not simply just a sequence of numbers. If we have a sequence of numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you say, okay, just that's the number representation you need, a computer can say, well, why can't I use 10, 9, 8, 7, 6, 5, 4, 3, 2, 1? Or why can I only use 5, 4, 3, 2, 1? So you need to give it direction to understand the LM, to understand how the words are worked and how they use in relations. So when you say I am vectorizing my words, that means you're grabbing these numbers and you're giving it direction. So again, I'm saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is east. Like you're going eastwards, right? So you're only using one direction to understand this concept. If you're writing Chinese who writes backwards, then you would have to use the other direction for it to be trained on, right? Because again, the words are going the other opposite direction. Meanwhile, in English, we know, or English is from left to right. So when you say tokenization and vectorizing, it means we're giving not only numerical representations, we're also giving directions of how the tokens work inside an LLM. So these word embeddings are complex mathematical models that use vectors, tensors, and weights to establish relationships between these tokens, and therefore create a context to collection of tokens. So when you grab these things and you convert it, luckily enough, you don't have to do this. So there's something called embedding models. So ChatGPT has their own embedding model. Llama has their own embedding models. There's open source embedding models. So this is what people have done during the NLP phase before LLMs happen, was to create these statistical models and say, that say, okay, he went to the store. What are the words that require the most attention? So you need to know, one, who is it? It's he went. That should have more weight to it, right? Because that's an action verb. So the action verb gets more weight added to it. To the, let's not give that much attention, because again, it's not that much important, but store is. So this is what it means when I say then when you embed these phrases and you're converting them into embeddings, it will show a mathematical concept we'll go through next, which shows you that what words get the most weight to them, what direction are these words going to, and all that, because they want to establish relationships, right? You're pretty much like training like a toddler to understand what are important to in order to formulate a proper sentence. So it needs to have these different rules of, okay, what direction is it going? What words need more intention? Which words need more weight? Blah blah blah. And each of these embedding models have these different types of things. So we'll go to the analogy next time. We'll go on the next slide from there. Yes. So we'll go through the tensors in these different slides. So don't worry. We'll go through. There's a lot of things to get through. That's the next. We'll go through tensors, the slide after this one. So let's go through an example. So we'll take the word, he saw the man with the phone. So we need to first convert that to tokens. So tokens are similar to a dictionary that contains thousands of words. And again, I'll give you a definition of word embeddings, the correct relationships. So he saw the man with the phone. So when you do a first step, your model, what it does, grabs that phrase and breaks it into different tokens. So he became token 1291, saw token ID 2847. It just assigns an ID to your words for it to know. Once you have those IDs of what words that has or understands what it understands with those words, it then becomes an embedding process. And how it works is, I won't go too deep into this because in RAG, and during the RAG sessions, we talk about this. There's different dimensions of your vector store you can go to. So you can have very small embeddings, which is 512 dimensions, or you can get very high embeddings, which are 1024 dimensions, which means that the more the dimensions in the embedding space just means how much detail you want to give it and how much attention do you want to give it. So the smaller the dimension, the less like the basic information it has. The higher the dimension, it could have more information because now you're putting more details, right? Like an example of this could be like he saw comma, oh, it had a comma here, so it was given embedding to the comma. This is between the third sentence, etc. As you go through higher dimensions, it provides more information, more context. So therefore, you could get higher accurate results as you increase your dimension size on your words. And as you go through the different business courses, you understand that if you're going to then use embedding processes that are higher, 512 versus the 1024, there's definitely a cost to adding because you're storing more information, etc. So typically you embed at a 512 dimension, and you're from there. So there's a mathematical representation of how you would do a vector embedding process, where E is equal to the embedding vector, WE is the embedding matrix, and X is the one hot encoded token. So we'll go through different examples of these mathematics. I know they might sound different. I don't think you're expecting a mathematical formula on a Saturday morning, but we'll go through what these mathematical representation looks like and how we use those during the tensor side. So when you look at this, it's the encoding matrix. Again, remember, I want you to go back and understand that these are concepts that were created, not new. This is things that we've seen that from 1940 that people were using matrices. If you remember that from your grade 10, maybe grade 11 math class, where you had a matrix of 101, 1000, and a table of 3 by 3, a matrix of maybe binary numbers. It uses those mathematical formulas to actually get this information out, which to me is extremely powerful in showing you that although I may have slept through grade 11 math because you weren't really that paying attention, but as you understand that each of these small mathematical formulas actually help and determine and predict future outcomes. So again, I think I talked about before, the purpose of doing embedding is to capture semantic relationships and cluster words. So example, king minus man plus woman is queen. So if you say the word king, if someone who is, for example, if you say who is part of the royal family, your predictive model is going to do a matrix and say, okay, say the word king, royal family, it's not a king, it's not a man, but we know it's royal, it's a woman, so therefore it needs to be queen. So it goes through a process of that information that way. Okay. Okay. So the question was a question in the chat about tensors. So tensors are these matrices that I was talking about. And there's different types of matrices that you can use in order to get your dimension space open. Again, my point today is to not have you go out and start building your own embedding models and getting on a pen and paper, like I'm gonna make the best embedding model. You could if you want to, I'm not gonna stop you. But the purpose is understanding what happens when you write something to an LLM model and how does an LLM model actually read it. And why is that important? And this actually goes back down to something called prompt engineering. If you're able to understand how an LLM actually reads the sentences that you're writing to it, what words it's giving more intention to, you can jailbreak LLMs. You can also have it give you more higher accurate outputs. You can have it activate certain areas of its memory better, understanding that if you were to write a word at the beginning of a sentence that gives it more weight and attention, that could give you higher results. That's in itself is super valuable. And this is the reason why I'm going through this information with you guys, to understand that if I were to write something ChatGPT is not seeing the actual conversation I'm writing to it. It's only seeing the embedding numbers being sent to it, and then it's going to go through its whole process. We'll get through the next part of the whole decoder process in order to get me the most predicted output information. So going back to this space, the tensor is a fundamental data structure that represents multiple dimensional arrays of data. So going back before, like I said, the grade level math, you see 1, 2, 3, 4, 5, 6. Each one is a separate row of areas, right? So if we remember a little bit more about matrices, what they do in these maths is that you can highlight directional, or you can go cross-directional, bidirectional, up and down, do multiplication of all different types to this in order to get a top probability. And that's what pretty much what they do when you use a tensors. It represents things in a multi-dimensional array and perform mathematical operations on them, and therefore establish relationships between the data. So you can have one matrices versus another matrices, and you have the word king and queen, and then it will do its own mathematical formula that we saw on the previous slide. Sorry, the W times E times X, and say, oh, there is a relationship between king and queen because they seems to be very highly correlated because of royalty. So again, the point of these things is to establish relationships between the data sets. And this is really the difference between an auto predict, an autocorrect, like an auto predict on your phone versus using an LLM. An LLM is actually actively trying to understand the context of the words you're writing by using vectors, using embedding spaces, and using the tensors. So one thing you need to know is that the better your word embeddings model is, the better your model is going to understand the outputs. So that's something to consider when you're working with these models and stuff like that. But again, if you're not building NLP models and you're not building an LLM from scratch, I wouldn't worry too much on developing your own mathematical formula, things like that. But this will really makes the difference between ChatGPT versus Gemini versus all these other LLM models that have come out, is because they use their own word embedding space. Remember, I told you before, they use their own word embedding space. So an example would be Llama. Llama went and trained its word embedding spaces on all the chats on the previous chats on Facebook. So it went on Facebook and grabbed and scraped everyone's conversations because, again, that's why Facebook's free. You guys are all the products. So anything you write on Facebook becomes their property, and therefore they used all that information to train their Llama model. And then when you start talking with Facebook or the Llama model, you're like, hey, this chat model is actually more conversational. Um, why is that? It's because they were able to create a better embedding model that could understand context and different things. Some of it because they were able to train this on better data and therefore were able to create better relationships between the words and make it sound more natural and fluid feeling versus a very cold robotic text that coming back to you from another type of a model that way. So this is what really makes the difference between these different LLMs and different models, is that they have their own embeddings, they have their own ways of how they're doing the multiplication to get into there. Another definition I really want you to understand is softmax. Softmax is really important in terms of generative AI. It's also used in machine learning, and it converts the output of a model into probabilities. So it takes all the vector numbers that we did, normalize them using weights, and you sum them up to the count of one. So yes, it's sort of like a statistics class right now. So if math is not your best subject, it's a fine, just stay with me. And I'm trying to make this as simple as possible. And again, I'm going very high level. I'm not going to go deeper into this, but I try to make it as clear as possible is that the softmax function is trying to grab all your raw scores from your matrices and your tensors, and then apply a weight to them so they all can sum up to one. The purpose of doing that is then you can quickly glance and see which words need the most attention. So he saw the man with the phone. So we could see here that saw was the one that received the most attention. With becomes the second word with the most attention. Phone and 18% becomes the most attention. So when this model looks and says, okay, which words I need to focus on the most, the softmax, what it does is simply takes them and pretty much normalizes them to all of them sum up to the weight of one. So softmax is a function that converts the output of a model into probabilities and are used to calculate attention weights in the AI model. So because of this, we're now be able to have weights and tell the model to say, okay, now this is what the person's saying. How do you want to output, right? So going back to realistic applications of this, if I said horrible man with a phone, that word horrible would probably get more of attention than the word man does because I'm giving something that could call the attention and from the softmax layer to that word more, right? Because what I'm trying to do now is trying to see how can I get better results. And this is where prompt engineering comes from, that term prompt engineers, is that you're trying to have it that when their model reads your response and when it hits that softmax application layer, it's able to give you the best probable results based off your responses. This is why when you write something to ChatGPT, you need to be very specific on how you need to write to it. And some people just write into it and say, oh, this is garbage. So let's say you're a writer and you love to write, and you ask ChatGPT to ask you help me write this poem, and it's completely garbage. And you're like, this is garbage. Like, I'm never gonna use ChatGPT again. But if you actually use prompt engineering and you change the attention weights and say, hey, you are now a professional writer. Professional writer will now receive the top attention in your model. I want you to write a 5-page poem. So again, the instructions will then receive more attention as well. And you must write in a very fluid and very coherent way. So what's going to happen? You've now given it more words to give it more attention to. So what's going to happen is if I go back into our model here, when you ask these different things, and you'll see that inside your model, you have a multi-head attention, that information is going to be sent by tokens into your embedding models into the LLM. The LLM has trillions of data stored and different parameters stored. So you'll be activating all of them and you're saying, okay, it's looking for a writer. So you have a huge note here of how to write stories. And then you have another note here that says need to write in what is coherent and fluid. And you have another note here of writing it very short. Combines and looks at all these different notes, uses the information now, and then feeds it to your softmax layer to figure out which one's the best response. And when that happens, you get a nice well-written paragraph, simply because you told it to write it as a professional writer, be fluid and coherent, etc., etc. You gave the right attention words to the LLM for it to understand what information nodes it needs to activate in order to retrieve the best response. So this is why it's very important when you write things to an LLM, it's not simply just asking for what you want. You need to be able to guide it, activate the right attention layers inside an LLM, and be able to activate the nodes that actually have the information that you're looking for. And this is why that's why prompt engineering is huge. We'll talk a bit more about that in the next next week. But this is where I'm trying to get down to the mathematics of why you're learning softmax. Why do you have to learn about tensors? Why do you have to learn about vectors? Is because you're using these probabilities, you're using these things as a way to get better results and for it to capture the information. And this is why it's super important for you to understand these type of concepts. Inside an LLM, you do something called linear projections. So going back to the tensors, what we have here is we have these matrices, all that goes through. Linear projection tries to reduce the matrix dimensions and potentially extract relevant information from the data. So there's different things that are happening inside your LLM model, not simply just taking the word embeddings, looking for the vectorization, that's it. When you go through the word embeddings, it's going to go through the different weights, right? And say, okay, this weight's here, this weight's there, this weight's there. You could have something inside your model that does something called linear projection, in which it gives more attention scores to different words. And there's different ways of doing it. So I'll just give a quick example of how that looks like. So example from here, going back to the same example, he saw the man with the phone. We have our word embeddings into a simple matrices right here. We can do a projection matrix, which will then, similar as we saw in the softmax layer, create weights for it. And from using those weights, you can then use it to project more information. The whole point of doing this, again, is that each LLM will work separately. Each LLM will have its own mathematical formulas. Each LLM will have its way to reduce cost. Linear projection is meant to reduce cost because, example, on the right side, instead of using a four vector sides, you can break it down to only two. And with less information to process, the cheaper it is, and the more results you can have. And the simple linear projections are ways to really break down even more different types of relationships, right? So, example, he saw the man with the phone. You could have different weights to be 0.5 and 0.1 are subject related. This one's action related. The phone is object related and waits for descriptions related. So again, in NLP, you're trying to create and derive all different types of interactions. So you're learning your neural network when you're training these data and having it can match up to the appropriate information. Because the whole point of it is that you want it to know your context. And this is the difference between when you're writing down like, well, how does it know? Like, how does it know empathy? How does it know how I feel? If I wrote ChatGPT right now, like my grandma just passed away, it's gonna give a weight for a subject, for the action, what happened, and descriptions. So it's going to show, okay, person is sad, needs to show empathy, empathy, prediction importance, and prediction relationships. And ChatGPT might come back and say, I feel sorry for your loss. How can I help you? So again, the whole point of it is to be able to use NLP, prediction, statistics, and mathematics to really break down the words in a language and help your model understand and mimic and replicate what a person could say. The one thing, again, I'll keep repeating and noting is that it's not learning for me. So although I may told it my grandma passed away today, if I write it tomorrow and I say this, if I say my grandma's running around now and having fun, oh, good. What is your grandma doing? Because it won't learn from my conversation. It's not meant, LM today aren't meant to be learning, evolving, and understanding. They're only meant, again, to only input text and output text. And how do ChatGPT and Claude people work a way around this is that they use something called conversation history. And what they do is every single time you interact with an LLM, they have on their backend file a running sheet of all the interactions that you had with your LLM, giving it personal informations, etc. That when you start a conversation with it, it actually feeds this conversational history to the LLM first, so it can understand everything about you, then answers and responds to your question. And it's not that LLM is learning Oh, well, I asked it yesterday. It's giving me this response. It's not because it remembered you. It's because they trained the model to first be sent a summary of your previous interactions and then your interactions happening. So it's being fed those two things at a time. So again, LLMs are not AGI. LLMs are not, they're not, they don't have consciousness, as most people are saying. They really are token NLP predictors that will react based off these word embeddings that necessarily need attention. Okay, so I will pause here. Any questions? I know I went through a lot of subjects, information, but anything from here from the group? Okay, it's a lot of information, so I'm glad that you're able to go through them. We talked about the difference between encoders and decoders, right? Let's go through some of them quickly. I told you in 2018, Google first made their own BERT model. This is an encoder-only model. So what this means is that this cannot generate text. It couldn't generate what was happening. Only thing it could do is classify certain subjects. So it could understand context, like I said, going back to the bank example. They could read a conversation of being you could send all information of a client having a conversation with someone else and say, please classify this. Then you can use a neural network like LSTM, things like that, etc., to sort of learn off previous interactions, say, okay, based off the embedding space, this conversation is mostly linked to Visa Gold, right? And the BERT model can then classify and say, okay, based off these embeddings, this one seems to be the most ones close to it. Based off these embeddings, this one's the most close to it. But you would have to feed it and give it all that information. It's not, it wouldn't be able to generate what the topics need to be. This is when GPT came out, generative pre-trained transformer. Which difference is this one can actually generate text. As you can see here, there are more steps to it. They're able to go in there and add in different types of attention layers in here inside the body. Because of these different types of multi-head attention layers, it's able to generate text based off the information that it has. So the information is being sent here. So when you ask an LLM a question, it goes through the encoding process, as you saw before on this side. It gives this to the multi-head attention weights here. Which words require the most attention to be looked at? Looks at its data, the pre-trained parameters, which data is the most related to this. Finds out which answer is best off your feed forward network, which we'll talk about next in a couple of slides. Gives it to your linear, which then makes it to a smaller matrices. Remember we talked about grabbing it 4 to 2 and actually showing the different types of verbs. Then we break it to our softmax. Remember our softmax is what we learned about of actually breaking the weights into one. Remember going from all the different types of matrices to now only a 1, 0, and everything between 0 and 1, and then gives that output of what the probable output could be. So we're slowly piecing together how this part is. There's still parts that we're missing we'll go through next. But you're slowly seeing now how this GPT works. Now, a transformer is when you combine a BERT model and GPT. So in Google created that 2018 model we saw here. And then OpenAI was just like, well, what happens if we grab our GPT model and combine it with a BERT model? What can we do? And they found that by combining that BERT model with that GPT model, which they built it off of, obviously because they just added a couple things to it, and they found that you could train a model on lots of data, have it classified, and then sent to their general pre-trained model, and then use that and become super smart. So they went through different iterations, GPT-1, GPT-2, then we got to GPT-3, in which we know we're at GPT-4 right now. But they noticed that by doing these steps and using these techniques, they were actually able to build this model. So really the catalyst of LLMs was Google DeepMind in 2018 by creating this BERT, which is bidirectional encoding retrieval transformer. And then you have your GPT that comes from that as well. So they say, oh, okay, cool, Google DeepMind built on this. What happens if we did this? And they found out they could actually predict. Then they combined it together in order to train really smart models together. Okay, so like I said before, BERT is a bidirectional encoder. So what does bidirectional mean? Remember we talked about vector stores, reading from left to right. So when you go through a BERT model, you can actually read from left to right or right to left. And so it's looking for any ways it can find a relationship between certain words. So then it uses these different rules to sort of in order to determine relationships. So BERT models cannot generate text. Remember, we talked about before, it cannot. The main goal of a BERT model is to understand the meaning and relationships within the text. That could only be effectively done with an encoder-only architecture. So a goal of the goal of the BERT model is not to generate any text, but to only really understand the concepts and understand things that are happening. This is why, in order for GPT to be done and really good, is then to feed everything that's happening in a BERT model to a GPT, so you can have that information going through. The purpose of the attention layer in AI is to establish relevancy of each word, giving each context. So again, I may have to go through this because we are running up really short in time, and we're on slide 25 of 50 that we have. But the purpose of these LLMs is to ensure that in these multi-attention mechanisms, it's able to understand the context. So you can see here that we have something called multi-head attention that we talked about. These are the ones that are being really important because these ones establish the relevancy of a word in a given context. So one thing that I want to note was before in typical NLP LSTM models, if the context was too long, the model would have issues dealing with words that are too distant in input context. For example, I'm getting overcharged. But the issue is I went to my grandma's house, and my grandma's house, she lost her card, etc., etc. But now that I found it, I want to go back and have a reversal on my credit card. In a real life conversation, you're going to hear a whole bunch of information that may not be related to each other. And the model only needs to hear lost card and the product that it was. But typical models would have an issue of saying, okay, but lost card was 50 words away from this product, so therefore it's not relevant. And that's really the issue that we would have before. But now with these multi-head attention mechanisms, you can say lost card receives the highest attention and the product that you have receives the second attention. So therefore you remove that concept of that distances by giving these sentences and words different types of attentions. Because the FFN, the feed forward network, is part of this. Remember going back to this part here, the feed forward network. So what happens after you get the attention layer of your words and your multi-head attention of your data sets? And it goes through it goes through that neural network and part of the transformer architecture. So again, as you can see, remember the matrices you can develop them in that way. I'm trying to explain this in the most simple way I can, but the point of this neural network is to extract any additional features that have been missed or uncover any deeper meaning or connections. So again, this is sort of the last bit of information that could be really important to it. So although we come here and we see here that we grabbed our attention layers from our test from our side, when we give it to our feed forward network, it's like, okay, but did you check this? It's like our last minute checker. It's like, well, did you really understand what this meant, etc., etc., etc. So it gives a last minute feed to check it. It grabs all the different relationships that are done there before it gets sent to the linear model, which then multiplies it all by the different relationships that it has. So the feed forward network is sort of that last minute subtlety check of uncovering any deeper or meaning or subtle connections. I won't go deeper into this. Again, I left this here for if you're more interested in that. And again, we'll talk more about that if you want to talk more about that in our weekly office hours. But again, you don't have to know all this information because I'm trying to give you a full direction of what this is. Okay, so we covered a lot of concepts. So we'll all come together when we review the transformer and architecture in detail in part 2. So there's a really great paper called "Attention is All You Need." This is when 29 I think it was in 2019, right after the BERT model from Google was done, and talks specifically all about this. So if you want to know more about how these attention layers work um, and really get deeper into this, really get that paper and "Attention is All You Need," and you'll probably get a deeper understanding of how the different attention layers work inside these LLMs. Correct. So someone asked, so there's no input for GPT decoder only. That's right. So VJ, to understand that is when we get to here, the GPT is a decoder model only. So when you have ChatGPT and you're talking to it, you're not feeding it any new information. So therefore, it's not encoding anything on the list. It's not using any encoding models in terms of classifying training data sets. It's only decoding your conversation and determining probabilities. And that's really the difference between those two. VG, but you still have your hand up. You can.
Yeah, actually, so but whatever we are prompting, like in the GPT, does it not considered input? So
So
this is the question, right? So anything.
yeah, I think it may be confusing with your input. So encoding model is only meant about how the model information it has. So when we're saying encoding, you're encoding training data sets to the model. So when you say a decoder, your decoder model is not consuming new data sets. It's not, like I said before, it's not self-learning. There's no new data coming in being trained into it. So it's not an encoding and decoding model. It's simply just a decoding model because when you talk to ChatGPT, you're not training new data sets and inputting it in there. But in terms of you inputting information into it, yes, you are. But it's not, and technically speaking, it's not considered encoding when you write your message to an LLM.
Okay, got it. Thank you.
So if suppose whatever we ask, if we need to retrain, they use a BERT model to add information to use it for the next question, for example.
Exactly. And that's what fine tuning is. So when
Mm.
you fine tune a model, you are going back and adding that BERT model to the side of it and encoding new information and adjusting some of the layers that are on the LLM. Awesome. Really great questions. Thank you, everyone. So I'm not going to go through this. We already talked about the tokens, pre-processing. There are more information about this. And again, you don't think you need to go down to scale dot product attentions during this area. This is more about that self-intention layer. Again, if you want to know more about the attention layer and get more of a deeper understanding of it, please read Attention is All You Need. It'll talk you about the scale dot product attention and how it actually calculates the attentions in words. But since everyone here, I'm sure that not everyone here is going to be developing an LLM. You just need to know that this is all part of the attention layers that are happening hidden inside the LLMs. And one thing that to show here is that there are multiple things happening at the same time. It's not just processing one time your conversation. It's looking at ways at more of 100 different ways of your language really get the best results coming out. Okay, so again, this is a little bit more about that. We already talked about the FFN. To summarize, we have input words coming in. We have it convert to tokens. These token IDs then become word embeddings, then become transformations. These transformations then get sent to the attention layer. Then the intention layer, it becomes part of the skill.product. Then it comes to softmax, and then goes for FFN. So that's pretty much, it's a common sense. It's not a common sense, but in the sense that it's a linear process of going in there. And what it does is part of the LLM is to really decide which of your conversation is most important and how it can predict the most proper way of responding to that. So here I put this in the slides as well, is what are GPTs good for? So they're good for, again, context generations. It can generate new text, etc. It is more expensive than a BERT model. A BERT model is not designed for fluent text generations, but it can be done for fast things such as classification, effective answer for Q&As, and precision text extracts. So each one sort of has their own pros and cons of which one they do. And again, the transformer model is to, again, train the GPT models and from there. Okay, so in Forbes, these AI prompt engineers earn 300K salaries. This was in 2023, I believe, 2024, early 2024 when these came out, right? So why are these engineers getting paid a lot of these monies, and why are they called engineers? A lot of people are just saying, well, you're just simply just writing instructions to an LLM. But as you can see, there is a lot more than simply just writing a simple story. You're trying to activate certain layers inside an LLM in order to retrieve the best response in its training data. So it's a prompt is that, so when I say prompt, for those who are just joining and understanding what AI, prompt is a set of instructions that act as an initial input for an LLM. It essentially defines the task you want the LLM to perform. It provides context, specifies the desired output of the information, and guides the LLM to a specific outcome, right? I'll go through a couple examples of that, but the effectiveness of a model reaction is dependent on the prompt quality. With well-crafted prompts leading to better outcomes, this is the importance of prompt engineering comes into play. So as these LLM models become smarter, I'm noticing now that I have to prompt less compared to what I had to prompt to, I would say, a year ago, last June. If I was last June, I was talking to ChatGPT, I would have to probably write at least a paragraph of prompt in order to get the output I need. I'm noticing today when I write to an LLM, I probably only need probably 2, 3 different sentences now in order to extract what I need. As these LLMs get smarter, um, I'm noticing that the prompting needs that I'm doing becomes less and less. So that's something to understand too as things go on, but you still need to use these prompts in order to get the best results. So example of this is, tell me the pros and cons of AI. You can tell ChatGPT that, even though a question is being asked in a prompt, it's still really broad in general. The model might give a generic answer it has on the first page of Wikipedia that it took out and then just regurgitates back to you. But then if you use an advanced prompt, you could consider a company using AI to automate its customer service, explain the advantage of this approach, that considers the potential disadvantages, and focus on customer satisfaction and privacy issues. So what do you think the attention layer is going to happen here? So again, it's going to give a major attention to automate customer service. It's the beginning of a sentence. So therefore, it's going to give it more of a higher viewpoint of what's happening. Then it's going to give another attention on customer satisfaction and privacy, saying, okay, I need to activate those nodes about privacy issues and customer satisfaction and get in there and then do this information. So as you can see, this advanced prompt is going to activate different nodes inside an LLM in order to get that best response, because you're feeding it different attention words for it to be notified. Okay, so what are the limitations of an LLM? There's a bunch that we talked about before, so let me just go over them quickly. Technological architecture, right? So the problem is that LLMs are running through statistics and math. So it's not that a it's not a problem in the sense that it's not going to give you 5 + 5, whatever it is. The problem that comes is that it's determining what is the most best response based off statistical and mathematical formulas. So if I were to say to an LLM, tell me why Michael Jackson is the best singer, it's going to write me a paragraph of why it is. But then I write it tomorrow and I ask the same question, tell me why Michael Jackson is the best singer. It's going to grade me a different paragraph, different introduction, same concept, but different words. But why? Like if the LLM is supposed to be trained on inputs and outputs and it's supposed to give me that information, why isn't it going to give me exactly word per word response that I got yesterday? And the reason why is because these models are considered something called non-deterministic responses. So the model architecture itself allows for varied outputs under initial conditions. So as much as you want to have it repeat the same word, you cannot. And this is what most people have issues with in production in their business because they say, I want you to classify these 10 documents in their prompts. And I want you to say you can only use only use these 10. Only use these 10 topics for you to classify these documents. Go. Then they get the output from the LLM, but guess what? It made up two different topics that weren't part of the 10. And you're like, what the heck? Why did that happen? Because the model, one is the context limit of how much it can consume and understand. And two, it's not built to be deterministic. As much as you want it to say, give me this consistently and tell me this, only give me these topics, it cannot because its mathematical outputs at the end is trying to determine what words are the most common relationships to that paragraph. So in itself, it cannot give you that. The only way to circumvent something like that is that you would have to write a custom Python function on it. There's something called Pydantic in Python, which you can give it a dictionary and tell it to only choose from the dictionary response. There's different ways, but you have to work around those. Like you have to create certain rules and Python and functions in order for it to get the response you need. So that's one huge limitation to LLMs is that non-deterministic. Two, the training data. If something is inaccurate in their training data set, and you have something coming out, or there's biases, or there's things that are happening, your LLM will then regurgitate anything that's happening in your training data set. So again, if something's wrong, it will show up in your responses as well. If the model, also the huge disadvantage of this is that these models are trained to give you an output no matter what. So let's say you put Neil Armstrong went to the moon, or did Neil Armstrong go to Mars? Neil Armstrong, space, flying, blah, 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 blah. Neil Armstrong went to Mars because although you may have not trained it on Neil Armstrong, it's going to try to determine and predict something rather than saying, I'm sorry, I don't have that information. LLMs are not developed to come back and say to you, I'm sorry, I don't have information. It's going to try to regurgitate something that is most probable to you as well. So this is the reason why we say LLMs hallucinate. There's a problem with these LLMs because their job is then to give you a response, although the response may not be there. Also, LLMs are considered black boxes. When you go back to the mathematical formulas in that multi-tension layer and that scaled out production, and it's multiplying, 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 it's multiplying, I said, over 100 times. So how do you explain to senior leadership why it chose to choose certain words with more intention and constraints? Is you can't, and therefore it becomes black boxes. So you're trying to be very careful of being able to say, I want to use an LLM for this because again, you can't back up a response of an LLM because of the black box things. Two, they're non-deterministic, and three, you're only good as your training data set ours. So there are these major limitations with these LLMs that you need to sort of work around them or find ways to work around to get the responses. And there are ways to work around, but we can talk about those and later on as well. There are some risks that also come that are happening in these LLMs. There's security risks. There could be tricked, attacked, or misused. Like I said before, if someone knows how to properly prompt engineer an ChatGPT or an LLM to extract information, they can do this, and we'll talk about those quickly. There also might be privacy data that's being trained on. I think ChatGPT is still being sued by New York Times for stealing their information and not using authorizations for their news place articles. So although you might have ChatGPT running into production, if they get sued and they're told to remove it, I don't know what that means for your business, and I don't know what the risk of using that is, right? So there are things that are happening that could be considered high risk in terms of using these AIs today. So here's some examples of these first runners of using AI. But these are major headlines in which these LLMs are getting in trouble businesses, right? So airline held liable for its chatbot giving passengers bad advice. What this means for travelers. I think this one, they told the passengers they can go in and return their tickets at a certain time. When they went to the front counter, they couldn't. And then they sued the airline. Everyone saying, nope, that wasn't our fault. It was the chatbot. But then they went to a court, and the court actually held up the customer's reaction. Well, this is your chatbot, so therefore you are held liable, and they were charged X amount of money for that. Second one, I told you, New York Times is suing OpenAI and Microsoft for copyright infringement. They're noticing that certain articles have been pulled from their website that has not been getting paid. They weren't paid for. They weren't given consent. They were just scraped without any given written consent. So we don't know what that means for the LLM itself. Also, these chatbots, someone tricked using prompt engineering to sell a Chevy Tahoe for $1, and it's going to the courts right now, because they're able to pass its guardrails and saying, well, your chatbot's saying you can sell me a chatbot, you can sell me a car for $1. This is your company, this is your data. I don't care if you didn't do things properly, but now legally, in terms of binding, you now have to pay me this, right? So these are things that these are things that LLMs have advantages and also have these challenges. So I'm going to pause there. We do have 20 more slides. I don't want to rush through them, so we can start them off by next week. But next week, I'll be doing a quick review of the architecture of the LLM, and we'll be doing another quick quiz about all the different concepts of this on their side. So that's sort of week one of concepts before we jump into week two. Hopefully, you guys are learning something new. Hopefully, these are concepts that can be really helpful and understanding what's really the pros and cons of using AI and LLM inside the business, and how you can sort of better your use of AI in itself. So thank you, everyone, and I'll stay back for 5 minutes for any questions.
Thank you, Luis.
Well, thank you for joining JJ today. Thank you for your questions.
Thank you.
It's very impressive. Thank you.
Thank you, everyone.
Thank you.
So, Luis, what do you do actually? Sorry, I missed the introduction like during the slide.
Sure, for sure. I'm an AI consultant. So I work for EPAM Systems, and I do AI projects for different companies across the United States and Canada.
Oh, for different companies, you do some AI. Okay.
Yeah, so like example, although EPAM is a consulting firm, so I work with different companies and do
Sorry,
enablement.
what is it? EPAM? EPAM?
EPAM, yeah.
Oh, mhm.
I also teach a college course here in Canada as well. So that's
Oh, yeah.
yes. How about yourself, BJ? What are you up to?
Oh, yeah, actually, I'm a statistical programmer. So for clinical trials program, I work in pharmaceutical data sector. but I'm curious about this AI and all, so that's why I just wanted to have some structured course like this. So yeah, if you have time, can you briefly mention about that capstone project, what we will be doing, what kind of thing?
Yeah. So the point of the capstone project is once you have sort of after week 2 and week 3, you have a little more understanding of how the code works. It's to think of something that you would want to solve using AI. So it could be something that you want to do for work using dummy data, or something you want to build just for yourself and be able to find out, hey, I can build my own chatbot, or hey, I can build my own classifier. Hey, I can build my own things. Something that you can feel more proud of the developing. And my job is to help you support you during that capstone project.
Yeah, thank you so much. Thank you.
No worries, EJ. All right, thank you for joining me today. Hope you have a great day.